Hello, my name is Brian Johnston, and I want to tell you about SomaGenics' recent work developing an RNA-based treatment for chronic diabetic wounds. This is my disclosure. Over 30 million Americans live with diabetes, and of those, 7.5 million will develop a diabetic foot ulcer. 800,000 of these will have an amputation, and their life expectancy is reduced to only 5 years. The annual cost of these ulcers is $13 billion in the US alone. And importantly, the current standard of care fails in half of these patients. Wounds are hypoxic, and in normal acute wounds, hypoxia elevates levels of HIF-1 alpha, a transcription factor that turns on a number of genes needed for healing. This pathway is defective in diabetics, and our strategy is to boost HIF-1 alpha by inhibiting PHD2, which under normal non-hypoxic conditions represses HIF-1 alpha. We accomplish blocking of PHD2 by using a therapeutic platform called shRNA, which SomaGenics developed and patented. It works in a similar way to siRNA, but has some advantages: simplified chemical production and purification, elimination of a complete class of off-target effects, and better inherent biostability. We screened for potent inhibitors of PHD2 and identified several shRNAs with low picomolar IC50s in cell culture, and as expected, they elevate HIF-1 alpha at both the mRNA and the protein levels. An unwanted side effect of PHD2 inhibition is, and HIF-1 alpha elevation, is upregulation of miR210, which impairs wound healing by reducing keratinocyte proliferation and mobility via E2F3. To counter this, we developed an antisense RNA, or anti-miR, against miR210 called SG608, which inhibits miR210 as shown in this luciferase biosensor assay. We then tested whether SG608 can increase keratinocyte proliferation and mobilization using a scratch assay. Either alone, dark blue bars, or combined with PHD2 shRNA, light blue bars, SG608 increased the rate of closure compared to nonspecific controls, yellow and gray bars. Whereas PHD2 alone, on the bottom chart, has, as expected, had no effect on keratinocyte movement. To deliver the RNAs in vivo, we used a technique called layer by layer, or LBL, which involves coating a nylon mesh substrate with alternating layers of positively charged polymer, followed by negatively charged RNA, generating up to 150 bilayers. If we lay the coated mesh into the wound bed, it biodegrades over time, several days, releasing nanoparticles containing the RNA in a form that it can be taken up by cells in the wound bed. Here's an example of placing cut-to-fit coated mesh material into splinted full-thickness punch wounds on diabetic mice, which have impaired wound healing. We confirmed that RNA is taken up into cells of the wound bed by fluorescent tagging of the RNA. And then we followed the closure of punch wounds in DBDB mice over 26 days. The LBL formulated shRNA, SG404, and the anti-miR 608 monotherapy treatments resulted in wound closure 4 days faster than either the blank substrate or nonspecific control treatment. The combination treatment led to a 5-day faster wound closure. When we looked at effects on downstream factors involved in wound healing at 2, 4, and 7 days post-surgery, both formulated RNAs, either separately or together, upregulate CD31 and Ki67. Because there's no perfect animal model of diabetic wound healing, the FDA expects efficacy testing in 2 different animal models. For our second model, we chose a rabbit with full-thickness punch wounds in the ears in the presence of neuropathy as well as diabetes. Our LBL formulated anti-miR210 substantially reduced levels of miR210 in rabbit skin wounds and accelerated diabetic wound healing versus empty substrate 4 days post-treatment. Here are the complete healing curves showing significant acceleration of healing in the rabbit model, and the dressings contained SG608 compared to substrate alone. To summarize, we've identified potent RNA inhibitors of PHD2 and miR210. The SSH RNA was taken up by cells in the wound bed when formulated with LBL. PHD2 SSH RNA stabilized HIF1 alpha and induced downstream genes involved in wound healing. Both the SSH RNA and the anti-miR are effective in promoting keratinocyte migration. We saw a therapeutically significant rate in abraded wound closure and reduction in time to closure in DB mice. We saw a significant increase in neovascularization and cell proliferation in the wound area. And finally, our anti-miR210 increased the rate of wound closure in the diabetic neuroischemic rabbit model. And finally, I want to thank these colleagues at SomaGenics and our collaborators at Stanford, MIT, and Harvard Medical School, as well as NIH for funding. Thank you.